Katrina Lidgard.
I'm Joseph Pierce.
I'm Grace Carter.
And I'm Weston Moz.
And this is our final project, the analysis of the unmanned aerial vehicle.
Since delivering packages by quadcopter could potentially cut shipping costs and time, our goal is to improve the stability of a quadcopter's takeoff transient response by comparing the quadcopter's height to a base and then using that information to alter the force applied by the rotors.
In order to optimize the dynamics of the system and account for the disturbance caused by gravity, our group has specified three main goals. 1. To minimize overshoot to ensure safe delivery. 2. To optimize settling time to efficiently reach a needed height without any oscillation. And 3. Disturbance rejection to combat the effects of gravity.
We found the equivalent impedance circuit for our system, and then we obtained the open loop transfer function from this.
This is the optimal reference height of our system that is compared against the actual height as the quadcopter takes off.
Looking at this transfer function, we chose our mass m to be around 1 kilogram and our b, our damping ratio, to be about 0.96 kilograms per meter cubed, because this is the air density at a mile of altitude in Denver.
We found that there were two poles for this system, at 0 and at 0.96. Therefore, this system can be modeled as a first-order system. The dominant pole is at 0.96, which corresponds to sigma. This means the settling time is equal to 4.792 seconds, and the rise time is equal to 2.29 seconds.
The poles will occur at 0 and in the left half plane. This means that the system is stable because there aren't any poles in the right half plane, but it isn't BIBO stable because of the pole at 0. This is proved using Routh-Horowitz as well. The dynamics of the system are not fast enough for the functionality of the drone. The open loop system also does not take into account that the system will need to overcome gravity, which will act as a disturbance. The reference input is the quadcopter's height.
To meet our requirements, we decided on the use of a PID controller. The parameters will each affect our system in different ways. The P controller will reduce rise time, but it will also increase overshoot. The D controller will increase stability and improve the transient response. And the I controller will eliminate the steady-state error while making the transient response worse.
The D controller will be the most heavily weighted because it increases stability and reduces overshoot. The I controller will be the second most heavily weighted because even though the system required a decreased steady-state error, the I controller makes the transient response worse. This is also needed for disturbance rejection. The P controller will be the least weighted, as reduced rise time is a requirement, but the system cannot sacrifice too much overshoot.
Implementing the PID controller, we get the following transfer function, h of s over h ref, as well as the disturbance rejection equation, h of s over f g of s.
To test the stability of the system with a PID controller, we performed the Routh-Horowitz calculations and found the following conditions that must be met for the system to remain stable.
Through an iterative process, we found the following values for our PID controller and the resulting outputs. Therefore, our final controller transfer function is going to be 1 plus 8s plus 1 over s, with the closed loop system shown.
Root locus shows the system is BIBO stable, now that our poles are off the zero axis. The Nyquist plot also demonstrates the system's stability because it doesn't encompass -1 and has no poles in the right half plane.
We modeled our system in MATLAB using the SISO tool, and found that our controller was actually more efficient than originally expected, because in our final modeling, we took into account the disturbance of gravity. The rise time of the system is 0.167 seconds, the settling time of the system is 18 seconds, and the overshoot is 4%. This is shown in our step response graph.
Now that our system is stable and rejects the disturbance of gravity, we can look at robustness. The gain margin is infinity, so the controller can increase any amount and the system is not in danger of becoming unstable. This can be seen in the root locus and the Bode plots. The root locus shows that as gain increases, the poles move to either a 0 or infinity without ever entering the right half plane. The Bode plot shows that the phase never reaches or crosses over negative 180 degrees.
The phase margin is 159 degrees, which occurs at a frequency of 0.365 radians per second. This corresponds to a delay of 7.6 seconds, which is a reasonable amount of delay for a quadcopter. Using the PID controller, we were able to design a more efficient and stable quadcopter that could be used to deliver and keep packages safe. Thank you for watching.